this part, we will overview game theoretic learning. Okay, so we will start with a single player with rested multi-arm Bandit. We will overview the upper confidence bound algorithm, the UCB, then the epsilon greedy algorithm, and then extension, which is called the epsilon n greedy. Then we will move to a single player restless MAB, which is called the RMAB. I will later explain the differences between the MAB, the rested MAB, and the restless setting of MAB. Under the RMAB, we will overview regenerative cycle algorithm, the RCA, then deterministic sequencing of exploration and exploitation, DSCE, and then our recent work on the adaptive sequential algorithm. Then we will move to model-free learning. We will overview reinforcement learning and deep reinforcement learning, and then we will introduce recent development of DRL on compressing DRL models. Then we will go to recent work, which is called the game of thrown approach. In this setting, we will consider multiplayer setting. We'll move from the single player here to the multiplayer setting in this model. Okay, so we will start with the single player multi-arm Bandit. So we will have a player which is who plays with multiple slot machines, and the player can get different return in a different slot machine. Each lever is an arm, and this is called the multi-arm Bandit problem with a single player here. And now the question is how to invest my money to maximize the return. So basically, if I would know which slot machine will give me the best return in average, I can invest all my money on this machine. But I don't know this, so I need to explore. And this is the exploration phase. So in the exploration phase, we need to try out each arm, which arm can represent action or option to get more information, so we can infer the best arm. The problem is that if we explore too frequently, then we spend time on suboptimal arms. That's what we do in the exploitation. So in the exploitation phase, we take the most likely best arm based on the information that we got so far that yields the highest reward. And the problem now is that if we exploit too frequently, so we will experience high error in inferring the best arm, because we can have errors, then we can have a loss that we want to avoid. So the question is how we balance this exploration versus the exploitation, which is called the exploration versus exploitation dilemma in online learning problems. So how we can efficiently balance these two phases. The performance measure that we use is the regret. The regret is commonly defined as the loss of an algorithm with respect to Gini with a side information. So to evaluate our algorithm, so we construct a Gini. This Gini has a side information on the problems, and then we want to evaluate how fast we can approach this Gini, how fast our algorithm can learn this side information. Okay, so the motivation to multi-arm Bandit's problems comes from a variety of problems, of models. So in our case, we are talking about a spectrum collaboration. So we have K channels. Each channel represents an arm, and then the player, which is the user, wants to infer which channel is the best one. So it takes observation and then learn online. Another example in networking, is the adaptive routing. In adaptive routing, we can route packets in multiple tests, and we want to infer which path is the best one. So we have multiple actions, and we want to infer which one is the best one. Another application is in financial investment. We can invest in companies. Each company is an arm, and then we want to infer which investment is the best one. So this applications has been studied in the literature, and there are other many applications. We focus in this talk on the spectrum collaboration problems, which map models these problems very well. Okay, so I will introduce what is map, what is stochastic map, and I will start with a basic formulation. So the reward of each arm is IID across time and arms. This is the model that we'll start with, and the optimal policy for Gini with the side information of the arm statistics is to play the arm with the highest mean reward. Now, the regret at time n under policy pi is the difference, the loss as compared to this Gini. So if we can look here, the regret at time n by policy pi that we construct is the difference between Gini that plays the best arm. The reward is n times mu star here. So basically mu star here is the highest mean. And we look at the difference. So this term is what our policy pi obtains during time. XITT basically is the reward that we get by playing arm IT. This is defined here. This is the arm that we choose, arm IT at times t. Now we can rearrange the term and get n times mu star minus this sum. This sum goes over the arms, which we count the number or the expected number of times that we explore, that we use each arm. So this is defined by ti pi n, the number of times that arm I has been chosen by policy pi at time n times mu I. And this is the regret in the stochastic map formulation. So why do we want sublinear regret? So note that linear regret can be easily achieved. If we choose a certain arm I, then the regret will be given by this term, n times mu star minus mu I. So linear regret can be easily achieved. And we want to achieve sublinear regret, because if we achieve sublinear regret, then the performance under our policy pi approaches Gini's performance as time increases. So if we look at this loss as compared to Gini performance, then we approach Gini. So the loss goes to zero as times go to infinity. And the goal is to obtain the fastest convergence to Gini's performance. So we want to best regret order. Now, what is the best that we can achieve? So Lyon Robbins has addressed these problems at 85, and they show that the lower bound on the regret has a logarithmic order. So this is the best that we can achieve. And now I will overview algorithms that achieve this logarithmic regret order. So I will start with UCB1 algorithm. UCB1 is the upper confidence bound suggested by Ower at 2002. And in this algorithm, we initialize the system by playing each arm once, and we observe xi1 and update the time to 1. So we played each arm one time. So this is updated to 1. And we got xi1. So this is the initialization phase. And then we run from t goes, this should be plus, from k plus 1, and so on. And then we solve the following problem. So what we look is on the sample mean over the excess that we observe at each arm. So we estimate basically we estimate the mean. So we have the sample mean here, plus this term. This term is 2 log t over ti n minus 1. So basically, ti n minus 1 is the number of times that we played arm I. So basically, if we didn't play arm I too often, this term increases, and then it increases this index, and then it makes us explore arms. As we choose the highest mean, then we exploit. So we see that this index balance between the exploitation of choosing the best term to the exploration where these terms got higher, and then we choose suboptimal arms. And this trade-offs between this exploration and exploitation phases. Now, Over show that UCB1 achieves a logarithmic regret with time and obtain this regret where delta I is the difference between U star minus the arm I. So we have these terms which depends on each arm. And the regret order is logarithmic, as can be seen here. So, okay, so this is a very popular algorithm, UCB1, and now I will introduce another popular algorithm, which is called the epsilon and greedy. So basically, the epsilon greedy was suggested by Sutton and Bartle in '98, and this is a randomized algorithm. So basically, we most of the time take actions with the best arms that we have, but we still explore suboptimal arms with a small probability, epsilon greater than 0. Now, the regret here is still linear because epsilon is fixed, and over at 2002, so the author extended the epsilon greedy by decreasing this epsilon with time. So basically, if this is the input of the algorithm, C and D, and without getting into too details, then we define a sequence of epsilons over time, and we choose the minimal between 1 and ck over d squared n, and then we look at this sequence which decreases with time. So we select the highest sample mean with probability 1 minus epsilon n, a probability that increases it with time, and play a random arm, which can be suboptimal, with probability epsilon n, which decreases with time, and the epsilon n greedy can achieve the logarithmic regret with time, as shown in this work by Over et al. So this is two very popular algorithms, and now I want to move to Markovian reward. In Markovian reward, the reward evolves no longer IEEE, but they have some Markovian rule with time. And in a rested map, we consider the case where passive arms are arms that we don't choose at a specific time t. In the rested case, the passive arms remain frozen. In the restless map setting, both active and passive arms evolve with time. So this is the difference between the rested and the restless. So this is what is called restless because arms that we don't choose also evolve as the arms that we choose to play. Now, the UCB policy and the epsilon greedy policy can be extended to handle rested reward processes. This has been shown in a paper by Tekin and Liu and by Zhao, a survey by Zhao. And we focus here on the restless case, which is more challenging and applicable to a spectrum collaboration problem that we focus here. So what about the application of the restless map setting to spectrum collaboration? So let's see at this setting. So basically, we have k channels, and the channels evolve with time. So basically, a user that wants to infer the state of the channels he can choose between these channels. And channels that the users do not use also evolve with time. So the restless map is very suitable to this case, to this application. And we focus on this model here in this talk. And we consider the case where in this model that the rate is markovian. Okay, so let's define the goal in our setting. So we want to find a policy that minimizes the growth rates of the regret with time, where the regret is defined by t times mu sigma 1 minus the expectation by policy 5 of RT. So the notation is as follows. So basically, we define sigma as the permutation of 1 to n. So basically, mu star is the maximal one, is the mu sigma 1, is mu sigma n is the smallest one. And RT is the total reward that the player gains over time. So it goes over n and over the number of times that we sample each round. Now, the regret, R phi t, is the difference between the expected reward that played by the arm with the highest mean minus the expected reward that a policy that we construct achieved. Now, note that this is a weak regret minimization because we limit Gini basically to choose the arm with the highest mean. And because in this RMAP setting, defining strong reward is intractable, then this weak regret minimization is commonly adopted in this setting, which can yield to tractable solution. It was introduced by Ower at 2002, and then adopted by Tekin and Liu in 2012, and Liu and Zhao in 2013. So basically, learning the restless Markovian reward statistics, it requires that arms will be played in a consecutive manner for a period of time. Because we have here a restless Markovian setting, this was observed in previous studies, which arms should be played consecutively with time, and the algorithm that was suggested to solve these problems was constructed based on these observations. So I will start with the first algorithm, the regenerative cycle algorithm, which is the RCA by Tekin and Liu. So in the RCA algorithm, we choose active arms based on the upper confidence bound index, on the UCB. So we play active arm consecutively, but we play it for a random regenerative cycle. This is the name, the RCA, a period, to learn the Markovian reward statistics. Since we need to learn this Markovian statistics, we need to play consecutively with time. And in the RCA, we do this in a random time, which is called the random regenerative cycle. The idea is to define a state, and once we start to exploit or explore, we first observe this predefined state, and then we continue by the exploitation or exploration phases. So I will not get into too details of this algorithm, but the regret was shown to be logarithmic with time under RCA, and it performs, as I said, regenerative cycle until catching predefined states. Now, this basically yields a heating time. So when we start to exploit or explore, we have a heating time until we hit a predefined state. And due to this property, the scaling with the mean heating time m is of order of O of m log t, which deteriorates performance of RCA in some cases, as we see. So then DSCE algorithm was suggested to overcome this issue, and introduce you the DSCE algorithm by Liu, and Zhao. And in the DSCE algorithm, we no longer play a random regenerative cycle, but we play arms for a deterministic period of time that grows geometrically with time. Now, a logarithmic regret was shown to be achieved under DSCE, and so basically the DSCE results in oversampling bed arms. Because we construct deterministic epochs of exploration and exploitation, we explore arms with the worst case, so with respect to the worst arm. And then the regret, although it's logarithmic, but it scales with this term. So basically, we have here 1 over square root delta, which is fine, but then we have another term, which is n minus 2 over delta, where delta is the lower bound over the difference between the arm with the highest reward mean to the second one. So basically, what is the corollary from this algorithm? So if we increase the mean eating time, for example, if we increase the number of the state space, or we decrease the probability of switching between states, then we increase the mean eating time, and this decreases performance under RCA, because in RCA at each epoch we start and we have a regenerative cycle until we catch a predefined state. So basically, if this increases the mean eating time, it deteriorates performance under RCA. On the other end, if we increase the number of arms n, when this term is small compared to other arms, then it decreases performance under DSCE, because the term that we have here this term n minus 2 over delta. So recently we developed the adaptive sequential algorithms to overcome these issues, and now I will describe this algorithm. So this is a joint work with my student, Tomer Gafni. And so the design principles of the ASR are as follows. So basically, we want to estimate online the desired unknown exploration rate of each arm, which is required for efficient learning. So it avoids oversampling bed arms, as in DSCE. At the same time, it avoids using these frequent regenerative cycles, and in RCA, as I will describe later. Now, the interesting thing here is that the size of the exploitation epoch is deterministic, but the size of the exploration epoch is random. So in DSCE, both the exploitation and exploration phases were deterministic, and in RCA, both the exploration and exploitation were random. Here we have exploitation, which is deterministic, and exploration, which is random. Now, the adaptive sequencing rules that decide when to enter each epoch, this is updated dynamically, and it's controlled by the sample mean, and it is done in a closed loop manner. And I will describe the structure of the algorithm now. So basically, these are the exploration epochs. And here is an example of exploring arm I. So let's see what happens in the exploration epoch. So we divide it to subblock 1, SB1, and subblock 2. And SB1, we first play a random period of time until we observe the last state observed in the previous exploration time. So let's take a look here. So if I start the exploration epoch here over arm I, then I play some random time until I catch this state, this gamma I, NOI minus 1, without getting into detailed notations. This term was observed here. So I look into the previous exploration epoch, observed this state, and then in the next exploration epoch of arm I will play this random time until I catch this state. So this is SB1. In SB2, the second phase, then we are playing a geometrically increasing deterministic period of time, and I will not get into details of how exactly to construct it. This is done in the analysis in the paper. So this is the structure of the exploration epoch. Now, what should we do in the exploitation epochs? In the exploitation epoch, these are construct here. We play the arm with the highest sample mean for a geometrically increasing deterministic period of time. And all the observation which we observed here in SB1 blocks then are removed to ensure the consistency of the estimator. So we estimate the sample mean, we play them in the exploitation epoch, but we remove this observation from our estimate. Okay, so now how we should decide when to explore and when to exploit. This is done by the selection rule. And what we wish to do, we wish to explore each arm I at least these times. And to achieve, this is the constant times log t. This is a constant, the leading constant to achieve a logarithmic regret. We show this in the analysis in the paper. But the problems that we have here that we need, L is a system parameter, and mu star is the highest mean. And this term is the mean reward of arm I, but we don't know this mean reward. So how we can solve this issue? We replace this mean by the sample mean and overestimate di. So we show that instead of looking at this term exactly that we desire, because I don't have it, so we replace this by the sample mean and overestimate di to ensure the desired convergence to the desired leading constant of the exploration rate. And then we explore on I whenever the exploration size is less than this term. This di is the overestimate of di. This is another constant, and times log t. Okay, so we show that in the paper that a logarithmic regret with time is established, is achieved, and the scaling with the mean heat in time m is now of order of O of m log t, which is very good. As compared, I remind that as compared to O m log t, which is obtained under the RCA. Now the scaling with delta, the difference, delta is the difference between the highest mean to the second highest mean. The scaling with delta and the number of arms is of order of this term now. So 1 over square root delta, as we have here under the SCE, but now this term is n minus 2 instead of n minus 2 over delta under the SCE, which is very good scaling with respect to the system parameters. And we show strong performance in simulations as well, in addition to this theoretical improvements. So basically in simulations, we simulate various settings. For example, RMAP with 5 arms, as we show that we achieve better performance than RCA and DSCE. Now, even if we increase the arms to 10, and then DSCE suffers because it explores with respect to the worst arm, then ASR still achieves the best. And now we played with the parameters. We decreases this delta, and again, DSCE suffer now, and we achieve better performance still. Also, when RCA and DSCE flips places here, and we also check the case where we increases the number of states, and now RCA suffers because of the too frequent regenerative cycles, and still ASR performs the best. So ASR performs very good in theory and in simulations, as we demonstrate. This is another example, and I will skip this. So far I discussed I describe algorithms which are model-based. Model-based algorithms, and we can achieve a strong theoretical performance. Now I want to move to model-free learning. So basically, which is now I will talk on reinforcement learning. So basically, reinforcement learning is a model-free learning. Now I have the agent, and I don't assume some model on the system model. The agent take actions, and it gets reward and observation from the environment, and the agent learns from the experience, and is not model-based. So, because model-dependent solution cannot be effectively adapted in general when to more complex models when we don't have a model, then this is it is desirable. And reinforcement learning is a model-free. It learns from experience, as I mentioned, and basically evaluating the expected utility among available actions does not require now prior knowledge about the system model. So now we will discuss this setting. So basically, what is the idea of reinforcement learning? So reinforcement learning idea is basically is based on a stochastic approximation. So we want to update a Q value of the game that we have at each time t for each action state pair. So let's take action S and A, state S, action A. Now we want to evaluate this Q value at time t plus 1. So basically, how we evaluate it, we look at the current valuation that we have, and now we add alpha times this term. So basically, this term is a learned value. So basically, what is a learned value? So here we have RNT plus 1. So RNT plus 1 is the reward that we get after taking action A and T. So we take action A and T, then we get this reward, RNT plus 1. We add gamma times max A and T plus 1, QT, S and T plus 1, A and T plus 1. So what is this term? Basically, now we moved to the second state. So basically, we got reward Rn after taking action A and T in state Sn. Then we move to the next state, S and T plus 1, and then we take action A and T plus 1. Which action we take? We choose the action that maximizes the future Q value that we see at the next state. So basically, this is the learned value that we will see after we take the action. We get the reward, and then we will take the best action in the next time. So this is the learned value, and we remove the old learned value, and this is like a stochastic approximation iterate update, and we do this to each state and action pair, and then we hold a table. So basically, the idea is to minimize the time difference, the TD error between the learned value and the current estimate value, and alpha is the learning rate, typically close to 0. And in this update, we hold then a table from a state and action, and then when we visit a state, we look at the table and know what the action that we should take to maximize this Q value. So this is the idea of the general idea of reinforcement learning. So reinforcement learning works well in small-scale models, but the problems comes with large-scale models. Because computing the optimal policy becomes intractable when the search space increases, it becomes inefficient from two reasons. The first reason is that as the problem, the dimension increases, then we need to store an intractable, very large table. This is one problem. The second issue is that as we have large-scale problems, many states are rarely visited. So, and then the learning becomes inefficient. And the idea how to solve these problems when we move to large-scale models is to approximate the optimal policy. How to do this? We want to replace this table that we had here in reinforcement learning by deep neural networks. And this is the idea of the deep reinforcement learning. So deep reinforcement learning, it uses deep neural network to map from state to action. So if we see here, we have some observation about the state, then we input this observation to a deep neural network, and the deep neural network outputs the value, and then we choose the maximal value. So it replaces this table that we described in the classic reinforcement learning. So deep reinforcement learning became very popular since DeepMind's Nature paper for playing Atari games at 2015. So in DeepMind's paper, so they tested hundreds of Atari games and showed very strong performance by using deep reinforcement learning. So the deep reinforcement learning solves two problems. One, the table is replaced by deep neural network. And the second is that deep neural network has the property which can represent well large-scale models. So we use these properties, and basically it achieves very good performance in large-scale models. Okay, so this is deep reinforcement learning, and now I want to describe our recent developments on a compact representation of deep reinforcement learning. So DNNs, deep neural network DNNs, they are typically over-parameterized. So they are large scale, they suffer from high computational cost and memory consumption. But if we use very large scale DNN, although works well, but it limits the use of DRL algorithms in systems with limited hardware resources. And this attracted very interested in industry in recent years, since we want to use automation, we want to use AI algorithm to use deep reinforcement learning models. But if we have too large deep neural networks, this limits the use of cheap hardware devices like Internet of Things, for example. In our problem spectrum collaboration, when we have simple chips that we want to operate a dynamic spectrum access. And this challenge has triggered a new and fascinating research direction, which is how to train deep reinforcement learning DRL models with strong and reliable performance, but we want to achieve compact representation of the DNNs. So basically is to take this over-parameterized DNN and to make it very compact. And the way to compress a neural network, deep neural networks, is pruning. Pruning is a very efficient way to do this. And pruning, the idea of pruning is to take neurons with low weight and quantize them, and then remove them from the networks. Then we can reevaluate and make the network to recuperate from the pruning and still make these networks work very well. Now, pruning has demonstrated very strong performance in supervised learning, but the problem is that pruning techniques do not work well in the DRL domain. But so what is the problem? Because the problems in deep reinforcement learning is that the ground truth is not given. Now we don't have label, we don't have the ground truth. So as we described in decision-making problems, we need to trade off between exploitation to exploration. And now when we want to do this on reinforcement learning problems, we must explore the state space in order to recuperate from the pruning procedure. And then we need to interact with the environment to get these values. Now, this leads to a significant instability in the pruning procedure and increases the performance loss. Now, the key to guard against losing a significant information regarding the optimal policy is to use the power of transfer learning and pruning in the DRL domain. So the key is to guard against this significant information loss, and that's the way that we do this. So basically, we develop the first effective solution for successfully pruning DRL models, and we do this by leveraging the power of transfer learning and use pruning to compress the DRL models. So I will describe this algorithm. This work was recently accepted to the IEEE Journal of Selected Topics in Signal Processing. It is in the reference in the end of the presentation, and we have the code is open source, and people, the researchers and developers in related fields of AI can download and further make improvements and upgrades. It is very easily to work with. So the basic idea is to first to create a teacher. So we start with creating a teacher with the large-scale DRL models, and now the teacher input experience reply with many experiences, and then when we move when we implement pruning, we developed a model which is called IPP, iterative policy pruning. Now the pruning is done to the policy, and now we no longer interact with the environment. So the idea here is to use to leverage the power of transfer learning, and we want to mimic the teacher. So we mimic basically the teacher from the experience reply and reevaluate the pruning procedure and recuperate successfully from the pruning procedure. Now, once we detect the redundancy in the network, in the DRL models, then we can shrink it. So this is the second model. We shrink the model and again recuperate with respect to the experience reply by the teacher, and then we get a shrunk model. Then we do this again. We have the convergence conditions until we get the minimal size that we can get, and we do typically we do this a few iterations until we get a shrunk model, a very compact representation. So I show here, for example, the IPP model, the output after one step of iterative policy of pruning, and we compared it with the popular pruning algorithm by Han, incorporated with Join Gupta algorithm of pruning. So basically, if we use the existing algorithm of pruning on DRL model, this is what we get. So this is the non-zero parameter of the neural network, and we can make it compact, but not too much. So the performance decreases significantly once we get from 1.6 million to 1.2 non-zero parameters. By contrast, if we use the IPP model, we can see that we're much more stable and can reduce the dimension significantly beyond this limit. So I now introduce some experiments that we did on popular Atari games. So the first example is on a Pong example, when we play tennis against the computer, and we start with a standard deep reinforcement learning model of 1.6 million parameters, and we compare our performance against the popular MBGP and KDBP. I will not get into details of this compression algorithms, but this algorithm, you can see if 18 was considered as a success in the mission. So this algorithm can reduce the size up to 20% or 6% at most. Now we run the POPs algorithm. POPs is the short of the policy pruning and shrinking, the suggested algorithm. Now we run the POPs algorithm, and in just few iterations, we got a compression of less than 1% in the popular Pong environment. We did, for example, another experiment over the Pac-Man environment. So again, the MBGP and KDBP could not achieve more than 7.5%, and we achieved in only a few iterations 0.26% performance, which was demonstrated a significant compression gain over existing algorithms. And Now, Amir will take.
Hi, I'm Amir, and I will continue Kobi's talk on game theoretic learning. So Kobi mostly discussed single agent learning, even in a multi-agent environment. And this is, as we discussed before, this is like this is like a competitive policy where the agent actually tries to optimize its own utility regardless of the other players, and that can lead to suboptimal performance in some cases. So to overcome it, people have looked at the problem of multiplayer, multi-armed bandit, where we have multiple players, there are multiple arms, and this is taken in Las Vegas. So we have like multiple slot machines, and we need to allocate people to slot machines because every person has different probability of succeeding in a given game as compared to the fully competitive setup. So early work on this was the musical chairs algorithm by Shamir and Rosensky. However, they considered a vector of utilities where all players actually have the same utility for each arm. And in the communication setup, we know that this is wrong. So let's see what are the specifics of this problem. So we have n players and k arms, and we assume here for simplicity that k is greater or equal than n. Actually, we can assume that they are equal. And at each turn, every player picks an arm. And this is the action an. A player that picks an arm no one else picked receives an IID reward, Rn of an. And whenever two players play the same arm, they will receive either 0 reward or they will get a collision notification if we are talking about a wireless channel, so they collided. We play for unknown number of turns, so we know that the game will end, but nobody knows when. Like winter is coming, but nobody knows when, or Corona will end, but nobody really knows what is the horizon. And the other thing is that player cannot observe the actions of the other players, and no communication between them is possible. So that looks like a very, very hard setup where actually no player can convey information except through collisions. That's the only joint information that passes between players. And the expected arm rewards are different between players. And they want to maximize the joint utility, which is the sum of the total rewards, and that is very different than optimizing each agent. So we cannot use a greedy algorithm that can lead to at least 50 to something on the order of 50% loss. Greedy approach will lead to something like 50% at least, but not, depending on the chance, it can be not much more. The other thing is that the game is unknown. Agents observe noisy utilities as part of the learning process. So each time you get a reward, but this is noisy. So you need to overcome this. This is the same like in the single agent. And as we said, exploration is part of the game. So whenever you explore, you lose. And the agents want to achieve a global social optimum, not just a Nash equilibrium. And that's pretty tough because they need to somehow jointly optimize a function which not even one of them knows. So that's a very challenging thing. So let's look at some definitions. So the instantaneous utility of a single player, Vn of AT, is Rn of ANT. This is the reward that it achieves times the non-collision indicator. So whenever there was a collision, it gets 0. If two players try to play the same arm, they get 0. So that gets into the reward in contrast to the single agent, where basically collisions are considered as part of the reward statistics. And that can be very different in terms of when the strategies are correlated. The total expected reward now is the sum over the optimal arm over n and t of the rewards, or the expected value of that, minus the rewards that each agent achieved over all times. So we sum both over agents and over time, and we want to maximize it. And remember, there is a correlation. If there are two players, two agents have very high utility on one, and on the other hand, the other player has half, and the other one has like 1 over thousands, then the one with half should take the worse arm, even if he has a bit more utility on the first arm. So that's, and somehow they need to coordinate it, and we will see how to do this. The reward process is independent between players, IID in time, and we assume that it has continuous distribution on 0, 1. Later in this series of talk, we will see other assumptions. All the results here actually apply also to Markovian bandits with more analysis. So I forgot to mention, this is a joint work with my student, Eli Bistritz, former student, he's now in Stanford. And this was presented in NIPS, and the full version will appear in Math of Operations Research soon. So what we propose is a game which we call Game of Thrones. So instead of a vector of arm expectation, which every arm has an expectation, which is same for all players, and you can play a musical chair just by sharing the arms between the player. Here we have a matrix of expectation, and the expected rewards serves as utility. Plainly thinking about it, it's a non-cooperative game, but we want to generate cooperation through the collision process. So each player actually needs a specific chair, specific throne. And if we assume that the utilities have continuous distributions, actually we know that with probability 1, there is a unique optimal allocation. Otherwise, we can randomize it in other setups. So there is only one optimal utility allocation of agents to arms. So the main result is like this: assuming that epsilon is small enough, we have a parameter epsilon, we need to be small enough, but actually simulations show that we're not so sensitive to that epsilon. And that the exploration phase, so we are going to define 3 phases. One is exploration, the second one we call Game of Thrones, and the third one is exploitation. So the length of the exploration should be larger than some constant n squared k divided by the gap square. And if we pick a delta greater than 0, then for sufficiently large t, the regret is less than 3 c2n log 2 to the power 2 plus delta t over c3 plus 2, which is basically of the order log to the power 2 plus delta of t, where A star is the best allocation of arms, A minus is the second best, and so J1 minus J2 is what Kobi called delta. Actually, the result with so much heavier math can be reduced to log to the power 1 plus delta, but it needs some more intricate analysis. So what is the basic idea? How do we solve it? So the idea is to use a basic result from Marden, Young, and Pao for distributed social optimization and adapt it to the Bandit context. So Marden, Young, and Pao propose some Markov chain that converges to the social optimum. And in contrast to their work, we only require to be with sufficiently high probability in the most probable state, which is the social optimum, under a stationarity distribution of a specific Markov chain that we are going to construct. The other thing is that they use the tree theorem to estimate the stationary distribution of the Markov chain that they construct. We cannot use it. We use it as a black box, and we will see the details in a minute. So what is the Game of Thrones? So let's get now to the game. So each player can have 2 mood state, we call it. It can be either content or discontent. If he's content, then with high probability, he stays in the same, he uses the same action. And with some small probability, he actually chooses a random, a purely random action. And this is used to generate an ergodic Markov chain. because all the states are now connected from every state, even if it's content. If it's discontent, his action is uniform along all the other actions. And now we need to see how do agents move from content to discontent, from discontent to content. So if the new action that he picked is the same as the previous one and the utility is positive, then a content player remains content and he stays in the same place. If he picked a different content, or his utility was 0 because of collision, or he was discontent, then he moved to content with small probability, and with high probability, he moves to the AN that he picked and remains discontent. So there is a small probability. Now, the point is that in Marden, Young and Pao, actually they needed some property called interdependence, which we do not need because we have the collision probability, and that replaces it. But this Markov chain, again, is very similar to theirs, except that the constants here are different, and this is not interdependent game. So this is what we call the Game of Thrones, and now we play epochs that are increasing in time, similarly to some of the solutions in Bandit, single agent bandits. So exploration phase for C1 phases, picking random arms, estimating the expected rewards based on the non-collision terms, including all previous exploration phases. So basically, we gather approximately linear number in time, linear in epochs, samples from each arm, and that basically converges the estimation error to 0 exponentially fast, which is important. The Game of Thrones phase, we play this Game of Thrones C2 to the power K1 plus delta, and the point is that this is also increasing, and that allows us to get into the stationary, close to the stationary distribution of the Markov chain that we defined in the game, that defines the Game of Thrones. And once we're at the stationary distribution, we can show that with high probability, we are at the optimal state. This means that we can pick the most probable state, the state that will spend most, and assume that, okay, this is the arm that we need to play in the exploitation phase, which takes exponentially large number of turns until the next epoch. So at each epoch, this phase increases exponentially, and that gives us the polylogarithmic regret. So why does it work? So the dynamic induces this perturbed ergodic Markov chain, and this tends to visit the optimal state more often than other states. Now, if C is greater than delta, this is sufficient to ensure that the state A star is the most likely. That's good enough. And when epsilon is 0, the Markov chain is a unique absorbing state, which is the optimal state. So when epsilon is low, even though the Markov chain is ergodic, it should, as epsilon goes to 0, it should visit more and more the absorbing state, which is the optimal state. And the proof exploits the tree theorem for stationary Markov chains, which defines the stationary distribution as a sum over all trees of many trees. And I will not get into the details, they are quite technical, they appear in the paper. And then we use the fact that collisions induce 0 reward to force player out of their current state. So this replaces the interdependence of Marden et al., and we basically use collisions. So putting all these together, we define the Markov chain, we show that the most probable state is the optimal. We need to show that basically the probability that we don't end with the optimal allocation at the end of the Game of Thrones phase decays exponentially faster than 2 to the k, which means that the probability of having error in exploitation phase is so low that this doesn't contribute to the regret almost nothing. Basically, by the Borel-Cantelli only finitely many times we will be wrong at the beginning of the exploitation phase, and all these phases are basically polylogarithmic, to reduce it to log 1 to the power 1 plus data, we need here to remove this. So we need to exploit previous plays of different Markov chains, and that's quite challenging. So let's summarize. We can see here that actually we converge quite fast to a good allocation compared to some heuristic algorithm that is known to perform quite well, the selfish UCB, which can be very bad in some cases. Of course, we are better, not much better, because this is an easy situation, but and we can see here the behavior. We see that these are the phases where the sum of utilities, the sample mean of the sum of utilities goes down because of exploration, but exploration becomes more and more rare. So that's how it works. And this is very surprising. We can get logarithmic regret or polylogarithmic regret when there is no communication between the agents. Okay, thank you. And we ended this part of the